Hi, this is the third session on compactness, part of topology series. We will continue looking at the examples in our list and find out which one of them are compact. Okay, so let's get started. So we had already seen various things, so let us look at now example. Okay, let X be with the co-countable topology. Remember, if X is countable, then we know that co-countable topology is the discrete topology, right? And again we have seen a discrete topology, discrete space is compact if only if it is finite, right? Therefore, when X is countable, co-countable topology, we already know all the details about compactness and non-compactness, right? So let us assume, okay, X is uncountable. Okay, first to make ideas clear, let me take X equal to R, right? Now what are the open sets? If I give you a non-empty U not equal to empty in subset of R, then U is open if and only if U complement, that is U complement is countable, right? So what is the obvious countable subset of R? For example, I can take N, right? This is countable infinite, therefore let's look at R minus U. This is open, right? Yeah, now you can see, to get, suppose call this, sorry, R minus N. So this is an open set which covers R almost except at natural numbers. So can I get an open cover starting with this? Yeah, so I can say UN, for example, equal to U union 1 to N or U union singleton. U union singleton. This is my U, right? Now let's look at, so each UN is open. Why? Its complement is a countable set. Only I am removing everything from n plus 1 onwards, or here I am removing all the natural numbers except n. Yeah, is this clear? Okay, now is it also clear R equal to union UN? Yeah, because remember, right, only in U what I am missing 1 to n. Okay, suppose X is in R, X is not equal to n, then X belongs to UN for all n, right? And if X equal to n, then X belong to UN. Yeah, therefore what do I here, what do I see? Therefore R is union of UN, therefore UN is an open cover. Now does it admit a finite subcover? Suppose it admits a finite subcover. Now you know the trick, right? For example, again it depends upon, let me look at my UN, the first case, union 1 to n, and suppose there is a finite subcover n of n, so that my R equal to union UN n in n. Now remember, now F is going to be finite subset of natural number, therefore it has a maximum. So let n equal to maximum of n in F. If you want it as usual, as I wrote in the one of the earlier cases, n1 to nk. Okay, f n1 10k equal to f. Right, now what do I know? Again notice that in the first case, this is the first case, as I said, my u's are my u's are as here, right? Then what do I have? un is contained in un if n is, okay, let me write uk is contained in un if k is less than or equal to n, right? Because what is un? uk has only one, apart from u it has 1 to k, whereas un has apart from 1 to k and k plus 1 up to n, so it has extra, right? Therefore in particular I will get r equal to union un, right? If r equal to union un n in f, and yeah, capital N is the maximum of f, okay, then this is what I get. But then this is wrong, because what does this mean? This is nothing other than r minus u, sorry, minus n union 1 to n. Therefore n plus 1 is an r, but n plus 1 does not belong to this. Therefore what do I conclude? Therefore un n in n has no finite subgroup. R1 also says does not admit a finite subgroup. Right. So what is it I have concluded? So I have produced an open covering of R with co-countable topology, which does not admit a finite subgroup. Therefore conclusion is R co-countable topology is not compact. Okay, pause, review, proceed. So this proof can be generalized to any set X which is uncountable. Okay, the trick is I can replace n by an element. Since X is it's uncountable, let x1 be an element of capital X. Okay, then x minus x1 is non-empty. In fact, it is still uncountable. Therefore, there is an x2 and so on. Therefore, and remember x2 is different from x1. And suppose I have selected x1, x2, xn, then remove this finite set x1, x2, xn. This is actually not empty, in fact uncountable. Therefore, there exists xn plus 1 here, which xn plus 1 is different from x1 to xn. Therefore, if I take A to be this set xn, okay, as n varies, now replacing n by A, and we can proceed as above. Okay, what will be your un? Un will be x minus A union x1 to xn. That's it. Okay, so I leave it as an exercise. So therefore x TC, the x is uncountable, and this co-countable topology is not compact. Okay, pause, review, proceed. Let us continue with the next example. That's a set with cofinite topology. Okay, so second example. Cofinite topology. So remember, X is a set, cofinite topology. U belong to that if and only if either U is empty or U complement is finite. Right? Okay. Now suppose ui I in I is an open cover of x, right? Now fix a p in x and p belong to x, that is union of ui. That means there exists a j in I such that p belong to uj, right? Therefore uj is not empty and uj belong to the cofinite topology. What does it mean? uj complement is finite. So that means x equal to u union f, where f contained in x is a finite subset. Sorry, uj. Yeah, okay. Now so for each x in f there exists ix in I so that x belong to u I of x, and that is contained in union ui I in I, that is equal to x. You understand? Therefore okay, look at the collection, the finite family of what sets? I should have uj, okay, and union u of ix as x varies over finite set. Yeah, this is a finite collection and this is an open subcover. This is a subcover of y. Yeah, you give me nx in x, then that implies x is in uj or x is not in uj, right? If x is in uj, then x is going to be there. If x is not in uj, then there is an ix so that x belong to u of ix. Therefore x belong to this flow. Yeah, therefore this finite subcollection is an open subcover. Do you understand this? So pause, review, proceed. So what have we shown? That you have shown that, okay, x with any set with cofinite topology is always compact. Okay, this is the conclusion. Okay, I hope you understand the proof. Okay, now let's look at the next example, because I'm just, as usual, I'm going through all our basic examples. Okay, so now examples are with the VIP topology where 0 is the VIP, right? Now what are the open set? If let us call it as tau VIP, then u belong to tau VIP if only if either u is empty or 0 belong to u. Yeah, right. Now what are the some kind of basic open set, simplest open sets? Non-empty, of course. They are of the form x comma 0. If x equal to 0, it is a singleton 0, of course, right, where x is in R, right? If x is 0, then the set is 0 comma 0, which is singleton 0. These are the open sets. Now can you think of an open cover, an obvious open cover? Of course, namely, let's look at this collection x comma 0 as x varies over R, right? In fact, I can say even this collection x comma 0 as x is in R star, that is R minus 0. because 0 is anyway going to be in these things. So this is an open cover. Okay, this is an open cover of R. Is that clear? These are all open sets, and any 0 always belong to this. If you want to call it UX. Right, then R is union of UX as X varies over R star. 0 belong to any one of the UX and X belong to UX, right? And this has no finite subcover. This does not admit right. That's very clear. Why? Suppose there is an F which is an R star, such that R equal to union X in R star of UX, sorry, X in F of UX, then what is this? Okay, what is this? UX X in F, where F is a finite subset of R star. This will be F union singleton 0. This is a finite set, because F is a finite set. 0. In fact, you even see it has no countable subcover, right? This actually shows. So if F is countable, then F union 0 will be again countable set, but that's equal to R. That's a contradiction, right? This is uncountable. This will be countable even if F is countable. Not necessarily finite, it's infinite uncountable. Okay, therefore this argument shows there exists no countable subcover, leave alone finite subcover. Pause, review, proceed. So what is the conclusion? Therefore R with a VIP topology is not compact. Do all of you agree with that? Now let's look at the next example. Okay, R with Outcast topology, where 0 is the outcast. So when does U belong to T outcast? Either U is all of R or 0 is not in U. That's it. You understand? Now suppose you tell me UI I in I is an open cover R. Right, now 0 belong to R, and this is union of UI I in I. This implies there is a J in I, so that 0 belong to UJ, but UJ isn't tau outcast, right? So when does, if 0 belong to U, an open set, then U must be all of R. That means that is UJ must be all of R. This implies UJ must be all of R. Do all of you agree? So what does that mean? Okay, it admits a finite subcover concept. In fact, there exists one UJ, at least one UJ, so that UJ is all of X. Therefore, what is the conclusion? R with Outcast topology is compact. All right. Okay. Now let's look at some more examples. Yeah. Now R with the lower limit topology. So when does u belong to tau L? If and only if either u is empty, or if x belong to u, okay, then x belong to, there exists a b greater than x, so that x belong to xb and b is contained in u. Therefore, if you give me x, then there is a b. This is open, this is closed, and this is open. Okay, right. So that must be contained, right? Now what you have shown, okay, is we had already seen any u in tau u, the usual topology, okay, then u is in tau L. That is, tau u is contained in tau L, right? Now we had already seen R with the tau u is not compact. For example, you looked at this collection minus n to plus n as n varies over capital N, and this is an open cover which has no finite subcover, which admits no finite subcover, right? Now this is an open subcover, open where? Open in tau u, and hence it's also open in tau L, right? Therefore this collection minus n to n as n varies over n is an, if you want, tau L open cover of x, and which has no finite subcover. Therefore, what is the conclusion? That is, R with tau L is not compact. Okay, pause, review, go through the proof. I am going to ask you a question now. Yeah, the question is, can you generalize this argument? So what really happened in the proof? That's what you have to think. Okay, what really happened? So I have a set X and I have two topologies, tau 1 and tau 2, and I'm assuming this is tau 2 is finer than tau 1, right? Then what I said is, if x tau 1 is not compact, implies x tau 2 is not compact. Do you see the proof? Because if this is not compact, there exists ui which are tau 1 open, so that ui is a tau 1 open cover for x which has no finite subcover. Okay, but remember, each, since tau 1 is contained in tau 2, ui is also tau 2 open subcover. And there, of course, there is no finite subcover. Yeah, if there is an f which is as a finite subset of I, so that union ui I over f equal to all of x, that's also a finite subcover, tau 1 finite subcover, right? Therefore, so is this clear? On the other hand, suppose x tau 2 is compact. Again, we are assuming tau 1 is coarser than tau 2, or tau 2 is finer than tau 1. Suppose this is compact, then I want to claim x tau 1 is compact. This must be clear, because if you give me a collection ui, I and I, This is a tau 1 open cover. What does it mean? It's an open cover. Yes, so that each UI is tau 1 open, right? But then this each UI is also tau 2 open cover, because each UI is in tau 2. But with x tau 2 is compact, therefore there exists a finite subset f of I, so that S is union I in F of UI. Therefore I found, since x tau 2 is compact, there is a finite subcover, but each UI is also tau 1 open to start with. Therefore what do you think I have found? I have found a finite subcover, right? So what are the results I have done? I have done that. Assume, okay, x tau 1 and x tau 2, and assume tau 2 is finer than tau. Then if this is non-compact, that is not compact, then this is not compact. And okay, and if this is compact, then we prove this is compact. Do you understand? If x tau 2 is compact, you've done. Do you see that? Okay. My next question: have you seen an analogy in this case of infinite series? Remember, you have if an and less than or equal to bn, these are non-negative, and let's look at the infinite series an and the infinite series bn. Right? This is a series of non-negative terms. The comparison test, what does it say? It says if this is not convergent, then this implies this series is not convergent. And on the other hand, if I know this is convergent, I know this is convergent. Right? Do you see the analogy? I hope you appreciate this. See, mathematics is fun if you try to understand the results which are analogous results. Okay? Yeah? Okay. Now, this immediately gives the next example. Let's look at R2 with the order topology. Okay, this is the dictionary order topology. So what we know on R2, we also have the usual topology or the metric topology. Okay, and what you have shown is this is not compact, right? But we also know, we have seen in the order topology video, that tau u is coarser than tau order. For example, if you take the basic open sets in tau u, they are of this form, right? Open ball. But if you take a point, any of these things, these are the basic open sets in the order topology. Okay, these are the basic open sets in the order topology. For you give me any point, there is this, right? Therefore we know these are all open in order topology also. Of course they are open in tau u. Therefore now we can assume, therefore the coarser topology, with respect to the coarser topology, the space is not compact. Therefore the final topology, namely order topology, is not compact. If okay, the conclusion is R2 with order topology is not compact. Okay, so now last example, okay, so something to do the metric space, because usually we also look at metric spaces. We have not done it, so let us do it now. Maybe I will change the color. Okay, right? So fix a point A in X. Using this, can you think of an open cover? Remember, on R, how did you think of an open cover? Minus into n. What is this? This is nothing other than B0n. Do you follow that? Now that is the hint. Now can you think of an open cover using this? Yes, you define un to be all open balls of radius n centered at A. Right? Now this un is an open cover. Right? Why? Because if x belongs to x, then let's look at dxa, the distance. This is greater than or equal to 0. Right? By Archimedean property, you see that I'm back to my pet obsession, real analysis. Okay, by Archimedean property, there is a natural number n, so that dxa is less than n. I hope you understand this. That is, n times 1 is greater than d times xa. Right? Given any real number, okay, x positive, then the nx greater than y. That version of Archimedean property is what I am using. Right? That means what? This x belongs to BAN. Therefore, x equal to union BAN. Again, we had already seen enough example. Okay, what is the relation between un and un plus 1? Because if I have x's in un, then distance between x and a is less than n. Therefore, it's less than n plus 1. And hence x belongs to un plus 1. Yeah? Therefore, this is an increasing sequence. Therefore, what is that you find? If x is compact, as if x is compact, okay, then since x is equal to union un, that is union BAN as n varies over n, okay, there is a finite subcover, and hence that means x is equal to BAN for some n, that is there is n a natural number. This we had seen, right? It's an increasing sequence and it's an open cover by means of increasing sequence of open sets. If it admits a finite subcover, okay, B A n1 n2 nk, choose capital N to be maximum, then it will be BAN. Yeah, the union, finite union will be contained in BAN, therefore it's equal to x. Do all of you understand this? So this in particular means x is a bounded set. Right? Or simply say x is bounded. So what have we concluded? We have concluded if xd, conclusion, if xd is a metric space which is a compact metric space, then x is a bounded subset of x, or x is bounded. So it's a necessary condition. Yeah, do you understand? This is therefore boundedness is a necessary condition. Condition for a metric space to be compact. Of course, it's not sufficient. Why? Let us look at. There are a lot of examples. I will give 2 examples and stop the lecture. The first example is, let us look at operand over 0, 1 with induced metric. The metric is the usual metric. Okay. Now this is bounded set, right? My x is this. Therefore x d is bounded. But it's not compact because we had already seen if I take 0 equal to, let's say un equal to 1 by n1, okay, again by Archimedean property, etc. But union un equal to x, that is 0, 1. Because if you give me an x positive, then there is n, so that nx is greater than 1. That means x is greater than 1 by n. That means x belongs to 1 by n1, etc, etc, etc. Okay, if x is, yeah, and it has no finite subcover. Okay, again by Archimedean property, this union has no finite subcore. Because if it has, again remember, okay, un is contained in un plus 1, therefore if it has a finite subcore, x must be all of un. That means it must be the form 1 by n 1. But if I take x equal to 1 by 2n, that's not here, but it is in the space, right? So this is, therefore this is an example of a bounded metric space which is not compact. The second standard example teachers will give will be where D is a discrete metric and X is an infinite set. So if it's a discrete metric, then the topology is discrete topology, right? And discrete metric is bounded because distance between any two points is at most 1. It's either 0 or 1, therefore it's bounded. But the topology we induced by the discrete metric is discrete topology. So what do you think? But we had already seen a discrete topology gives rise to compact space if and only if the set is finite. But what is my assumption? X is infinite, therefore this is bounded metric space but not compact. Okay, so pause, review, proceed. So that more or less completes a lot of examples we had already gone through. I think this is more than enough. Okay, in the next lecture we will talk about compact subsets. Meanwhile, you should think about how to define, when do I say a subset A of a topological space X is compact. Okay, how will you define a subset A of a topological space is connected? Do you remember that? Yeah, think about. We will come back with that definition in the next lecture. We will complete. Stay safe, take care.